This video is supported by the National Science Foundation.
Hello, my name is Olivia, and I am a member of the Florida Institute for National Security at the University of Florida. I'm here to present a tutorial on reverse engineering integrated circuits from scanning electron microscope images using artificial intelligence for hardware assurance. The main objective of this module is to complete a project on hardware reverse engineering using artificial intelligence, or AI for short. To help guide your project, the next few lectures will be delivered hands-on tutorial style. We hope this project will be beneficial for you as a resume booster that you can use when applying for a job or for further education or professional development to support your existing position. Topics that will be covered in this module include Python programming language for AI, image processing and computer vision, and machine learning. In this lecture, we will be introducing the IC SEM RE problem and setting up for a code pipeline for the project. This video assumes you have some prerequisite knowledge of Python and hardware assurance, so if you do not, please refer to the prerequisites in the description. This tutorial is best if you follow along with me, so feel free to pause, rewind, or slow down this video at any point and refer to the documentation whenever a new method is introduced. If you would like to follow along with me, I will be using Jupyter Notebook and adding things to my desktop. Here, we are going to want to upload our data, so the link to this will be put in the description. For me, it ended up in my downloads. We want to add GT0 and IMG0 and upload. Next, we want to add a Python 3 kernel. You might find it helpful to name it something to the respect of Lecture 1, for example. For this tutorial, we will be using the following Python packages. NumPy provides the ND or n-dimensional array data structure to represent and process image data. Matplotlib will be used to visualize our images. Scikit-image contains algorithms and tools for image processing and computer vision. And scikit-learn contains algorithms and tools for machine learning. If you are interested in learning more about these libraries, links to their websites can be found in the description. Let's import the libraries. So we want to import NumPy as NP, so we don't have to write out the word NumPy every time. Next, we want to import matplotlib.pyplot as plt, so you don't have to type out the word pyplot every time. Import skimage and import sklearn. Hopefully, it should run. Okay. That's just a warning. We can ignore it. Quick overview of our goals. We want to be able to segment or separate out the foreground, or the regions of interest, from the background, or the regions that are not of interest. To accomplish this, we need to somehow generate a binary image where the foreground pixels are distinctly marked from the background pixels, like this. As you can see, the end goal, known as the ground truth, has two values: true, or 1, for the foreground, and false, or 0, for the background. A human subject matter expert worked very hard to provide us this ground truth data. Unfortunately, this is only a small part of the problem. You see, the human subject matter expert spent a great deal of time, effort, and resources to manually label a small portion of just one image. To reverse engineer several complex integrated circuits, we need to somehow segment multiple scanning electron microscope images. It is slow, expensive, and impractical to task a human or even multiple humans with doing this manually. Therefore, we have been tasked with segmenting these images automatically using artificial intelligence. So first, we need to gain some domain knowledge or context of the problem. Let's take a look at the original image. To get a better idea what's going on, let's go ahead and take a look at the original image. So the original image is saved as img_0.png, and it looks like this. So we want to be able to read this in our code. So we can do image equals skimage.io.imread and the file name. So it is in, since im0.png is in the same folder, we can just give it the name. So img_0.png. And to show the image, we want to use matplotlib. So up here, we named it plt. So we'll be using plt every time we want to use matplotlib. So plt.figure, plt.imshow, the image, and then plt.show. So hopefully this runs, and it looks weird. So as you can see here, this is in gray, but this is obviously not gray. So that's the color map issue. So in the IM show, I think we need to use CMap equals gray. I think it's AY, but it might be EY. We'll see. Oh, perfect. It is AY. So now we have successfully loaded the image into our Jupyter notebook. Next, we want to print some image statistics. So first off, we want to know what is the type. So type let's run this. It is a numpy.nd array. So n-dimensional array. Here it's 2-dimensional. Okay, so nd arrays have a d type. So you can type image.dtype. You can also print off the shape. So shape dot shape. So as you can see, it's uint8, which means that the values can theoretically range between 0 and 255, and the shape is 800 by 800 pixels, so that looks about right. It gives us the values here. So let's see if it's actually using the full range. So we want to know what values the pixels actually are. Range. And we can use numpy for this. So numpy.minimum to the maximum. Run this cell. So it looks like this particular image is using the full range of 0 to 255. Now, these image statistics are used a lot, so let's make this into a function. I cannot anticipate having to use this. So doot, plop it here. Let's take this here and make our own function. Def, let's call it our own im show. Let's call it image dot. It is a numpy or nd array, so 2D. And then it's a good idea generally to give everything a title just so you know what it is. You don't have to, but it's a good idea. And let's make this into a string, tab, so it actually stays inside of the function. And let's give it an actual user title. Now we can use our own custom im show. So im show. And it's generally a bad idea to name your variables as the parameter names. So I'm actually going to name this original image. and we are now going to IM show the original image, and we need a title. So just gonna call it original image. Now we can run this. So we have the figure title, we see what it's looking like, and it is successfully printing off all the statistics. And that's just a quality of life thing. We're printing off statistics pretty regularly. It's a good idea to make your own function. One of the most naive approaches to segmenting an image is simple thresholding. The algorithm is as follows. Pick a threshold value, or in this case, a number between 0 and 255 because that's the range of the original image. Then, for all pixels in the original image, if the pixel value is greater than or less than the threshold value, mark it as foreground. Otherwise, mark it as background. Here, the regions of interest, or the foreground, are generally brighter than the background, so we're going to use greater than. Following up, we now want to segment our original image. As a quick reminder, we defined a function called IMShow, and we have our image saved as original image. So for the basic thresholding, we want to set a threshold. So threshold equals the range is from 0 to 255, so I'm just going to pick a threshold in the middle. So for example, 128. I just randomly picked that. You can pick whatever number you want between this range. To do the threshold, the segmentation result will arise when you take the original image and all pixels that are greater than the threshold should be marked as true, and all that are less than the threshold should be marked as false. So let's show this. Live typing is difficult. And hopefully this runs. So this is a segmentation result. As you can see, it's a lot of black and white. So we can confirm that is now a Boolean image. So Boolean meaning there's only two values. The shape is the same as before, but the range is now false to true. So true would be the pixels that are bright, white, or also 1. False is dark, black, also value 0. So as you can see, 128 wasn't a very good number. You can play around with this, maybe try like 120, anything you want to play around with. Oh, that actually doesn't look too bad. So play around those numbers. There's a way to evaluate this in the future to make sure that the value that you have is good. Now that we have a segmentation result, we want to know how good it is. In other words, we want to quantitatively evaluate our segmentation result. One common evaluation method is the intersection over union, or IOU score. This is a little bit hard to see, so let's zoom in a bit to see what's happening visually. After segmenting the image and obtaining a segmentation result, we want to compare it with the ground truth. When comparing the segmentation result to the ground truth, there are two values of interest to us. The area of intersection of the two and the area of the union of the two. The IOU score is then taken as the area of intersection divided by the area of the union. Because of how the score is defined, the IOU score ranges between 0 and 1, with 1 being the best and 0 being the worst. Now that we have a segmentation result, we want to compare it to the ground truth. So first, we need to load and show the ground truth image. So ground truth, we can load that in the same way we loaded in the original image using skimage.io.imread and we named it ground truth underscore 0.png, and it looks like this. So ground truth underscore 0.png, and we want to show it. IM show ground truth, and let's name it ground truth. And hopefully this once it does, and it looks about correct. And it read in as uint8 0 to 255, whereas our segmentation result is a boolean with values false and true. So this can be easily remedied when we read it in. We want to do as type boolean. Run. And now it is properly a boolean. Now to evaluate and compare the ground truth with our segmentation result, we want to use the IOU score. So we have to import another library. So sklearn.metrics. And we need the IOU can be equal to sklearn.metrics. It's called the Jacquard score in sklearn metrics. Let's move it up so you can see a little bit better. So the IOU is actually a specific instance of the Jacquard score, but for 2D inputs. The Jacquard score is the more generic version. So we want to compare the segmentation with the ground truth. And then we want to print it off. And hopefully this one's not happy. Why are you not happy? Oh, as I just said before, the Jacquard score is a generalized version of IOU. It is not expecting a 2D input, so we need to flatten things to be one-dimensional. And now we run. Okay, so the IOU score for our result is about 0.477, which is fair, but it's really not great. The best score is 1, so it's doing kind of bad, actually. Let's see if we can visualize some of these results. To get a better view of what's going on, let's see if we can kind of superimpose our segmentation result over the original image. So visualization, let's use skimage color labeled to RGB. Moving up so you see. And we want to compare or overlay the segmentation over the original image. And now we want to IM show. And then result overlay. And hopefully this one's. Okay, I'm colorblind, and also that's way too big. Let's see if we can change the visualization screen. It's very hard to see this, so let's do just 0 to 100 maybe. Yes, but I'm still colorblind. So let's change this. The color can be changed to, I think, yellow. Oh, much better. Okay, so as you can see here, Whatever the segmentation result thinks is the foreground is in yellow, and it's superimposed on top of the original image. So as you can see, there's a lot of noise in both the background and the foreground. So we want to see if we can fix this in future lectures. In summary, this is what we covered today. We introduced the reverse engineering problem using scanning electron microscope images of integrated circuits for hardware assurance. We applied simple thresholding as a naive segmentation technique. We applied the intersection over union score to evaluate our segmentation result. And in the next video, I'll be expanding upon our work here using a more advanced image processing computer vision approach. Thank you for your time.